Good afternoon, everyone. My name is Rangelov from Danfoss Global Applications team. Today, we'll be looking into how to optimize performance of a CO2 heat pump in industrial applications. Please place your questions in the chat below, and we'll look into them during our Q&A section at the end of the session. Let us look into the agenda for today. We'll start through the basic system architectures for CO2 heat pumps, which we see in the field. Then what are the major efficiency factors for CO2 heat pumps. Then go through what is important during compressor selection for CO2 heat pumps, and also the rest of the components which play a role for performance in heat pumps. Let us go to the system architectures. Here are the basic 4 layouts for CO2 heat pumps. The simplest one in the top left corner, where either air or water can be a source with certain temperature, which is being lifted by one-stage compressors to the required by the gas cooler temperature and pressure, which heats up water with a certain return water temperature to the required by the heat sink supply water temperature. Then the CO2 gas is being throttled through the high pressure valve into the receiver, where the liquid has been expanded to the evaporator, and the circle repeats and repeats. The COP of this system is our reference for the slide. First improvement, and a minor improvement of this layout, is considered only internal heat exchanger, which is placed on the IT receiver section, but it can be also placed instead different places in the system. First bigger improvement of the COP can be made by adding a parallel compressor, which has suction connected to the receiver level, by which it removes or it takes flash gas from the receiver level and compresses it to the gas cooler level, by which we control the receiver pressure and unload the empty compressor levels, which is connected to our evaporator. Or with other words, we have suction at a higher pressure level, and by this we gain, according to industry sources, efficiency improvement of around 7%. Another improvement of efficiency of this layout can be done by integrating a high pressure lift ejector, which also, just like the high pressure valve, retains the pressure into the gas cooler, but it utilizes efficiently the pressure difference between gas cooler and receiver, which creates kinematic energy, which creates under pressure in the connection to the evaporator, which is shown over here, which takes further flash gas from the evaporator and sends it to the receiver. So once again, we unload the empty compressor level connected to the evaporators, and we load the higher suction level, the parallel compressor. Industry experience tells us that improvement is further expected of 5-6%, which means in total 12-13% better performance compared to our reference system. Another way to utilize ejector technology in transcritical CO2 system is the low pressure lift ejector in the bottom right corner, where you may see also a simplified layout where we spare a compressor, because now the ejector is able to circulate or to take the whole flow from the evaporator and compress it to the receiver, or take the whole lift between receiver and evaporator level. Nevertheless, as the name suggests of this ejector, low pressure lift ejector is corresponding to lower lifts compared to the high pressure one. In this case, 5, maybe 7 bars difference between receiver and evaporator. However, we can have a suction of a higher flow rate. This is a typical system which we would see in water-to-water heat pump. The high pressure lift ejector, it can lift up to, let's say, up to 14 bars, and nevertheless, it can circulate, it can take a lower amount of flash gas from your evaporator, but it can support with higher pressure differences between evaporator and receiver level. This is typical layout seen in larger commercial heat pumps or industrial size with air as a source. These are the four basic system architectures for CO2 heat pumps. There are various combinations between them, but we can boil the fundamentals to these four, at least when we talk about heating. Nevertheless, we can combine heat pumps and talk about combined cooling and heating. An example would be for industries such as food and beverage, where you have both refrigeration requirement but also heating requirement. For the former one, we have a cooling system, but for the latter, typically fossils are burned. We can decrease substantially the use of fossils or completely disconnect from them if we connect cooling and process heating together. An example can be in a plant where we have in this layout two temperature level for your cooling system, and instead of rejecting the waste heat into the ambient air, we can lift it to a useful level in a heat reclaimed heat exchanger gas cooler where we heat up water for processes which can be stored in a tank. One of the challenges of this type of layout is load balancing. You don't always need heating when you need cooling. Therefore, when you shut down the heat reclaimed heat exchanger, you still need to have a backup gas cooler, air cooled, the easiest, so your refrigeration system can work independently of your heating system, and vice versa. If you have part load in your refrigeration cycle, you may not have sufficient amount of waste heat for your heat pump. Therefore, you need to consider additional heat source, a backup evaporator, whether air or better water would be a source, but this needs to be accounted for. So we need to have a flexibility in operating systems for combined cooling and heating. We need to control them smartly, and load balancing is a key over here. This is talking about the refrigeration circuit, but there are important factors also outside of it. One of the most important one is the return water temperature. We have, for illustration purposes, made several simulations on one of our transcritical CO2 compressors. Namely, we would like to show how the COP of heating varies, and also the compressor's thermal capacity as a function of increasing gas cool outlet temperature in the range of 77 to 122 F. And namely, in that range, the COP loss is around 40% and capacity loss is something similar, which, based on this picture, tells us as a rule of thumb that CO2 may be challenged in its performance for return water temperatures above 105, 110 F. This assumably may end with gas cooler outlet of 120 F, which COP is not that great, and also the capacity of the compressor is not very high. So you need more compressors, and they'll not work very efficient. So this is not too good. How does CO2 benchmark with other popular refrigerants for cooling and heating? We have tried to make a pointer of which COP is higher between ammonia and CO2 in a chart, which is a function between water supply and water return temperature. There are various assumptions made for this study. This is only static simulation of a heat pump with an air source of 41 F. The results are valid only based on the specific assumptions. Not all of them are listed. If you're interested to hear more, please reach out to us. We'll be happy to share and have a discussion. This is made only to illustrate a picture here. And so far, the results tell us that for the lower temperature lifts, one-stage ammonia is dominant in the COP. When we have a little bit higher lifts, then two-stage ammonia is required, either because one stage is challenged by compressor envelope limitations, or because it is just much more inefficient than two-stage ammonia. And for the highest lifts, we see that CO2 is actually having the best COP over here. We cannot stretch enough how important are the assumptions here. These results are only to be serving as a rule of thumb and are valid only for these specific assumptions. I also have to add that our assumptions on the superheat of the evaporator, I believe, are a little bit conservative. They're outdated. They're based on superheat of in the range of 18F in the evaporator. We see that more or less all rack builders on the field, all contractors, they use evaporator superheat of 9F, but there are some state-of-the-art CO2 manufacturers which can go to significantly lower than this, and they can go to a slow pinch between evaporator suction SST and ambient air as low as 7 Kelvin, which is 15 F, if I'm not wrong. In this case, if we take these assumptions, then you see that CO2 becomes more efficient in a significantly larger area. Again, it is the same concept. Higher lifts, lower return water temperatures, but with proper superheat or evaporator superheat control, we can really gain a lot of efficiency improvement in your CO2 heat pump. How does CO2 looks compared to other refrigerants which are popular for heat pump systems? We have again made some simulations for air-to-water heat pump where we fix the source at 41F and we vary the supply water temperature, where we study COP of 1 and 2 stage ammonia, also propane, isobutane, cascade between both, ZE refrigerant and CO2. Looking into the graph, it becomes obvious that all systems besides CO2 decrease their COP with the increase of the lift. This is logical since they operate in subcritical mode. In this mode, you need to increase the pressure in your condenser in order to reach the temperature level required by your heat sink. One of the unique parts of the CO2 is that its COP remains constant during these conditions with a fixed water return temperature at 204 F. Why is that? It appears constant because the water supply temperature can be raised to high temperature, let's say 9 F below compressor discharge, without necessarily to increase the gas cooler pressure. So you don't penalize the compressor with additional power consumed. This is unique about CO2. We also have to add, it is important to have a properly sized and functioning gas cooler. So heat exchanger selection is critically important. So again, in these conditions, we see that the break-even point with most refrigerant is at a high temperature lifts, and the highest is already challenging the most efficient refrigerants. What happens if our return water temperature was fixed of 95 F instead of 404 F? Well, then we see improved COP, which now is able to challenge most refrigerants already at a lower temperature lifts. If the return water was further lower level of temperature, then CO2 becomes actually extremely good, extremely attractive refrigerant, which is challenging, even the most efficient ones. What happens if we now fix the water supply temperature and vary the water return? So if we fix the water supply at 176 F, we have all other assumptions like the previous slide. Then we see that for the lowest water return temperatures, CO2 is actually the most efficient refrigerant. Nevertheless, its efficiency decreases very rapidly with the increase of the water return temperature. In this case, for our assumed conditions, 2-3% loss of performance per 1K increase of the water return temperature. All other systems remain almost completely stable. Ammonia declines a little bit its efficiency because in our assumptions we have calculated rather large subcooler, which is typical for ammonia systems. So we're still somehow connected to water return temperature, but not at all it's in the same scale as CO2 systems. So designers which have possibility to use very low return water temperature may see excellent opportunity in CO2. Nevertheless, we have to be conscious because if we have a buffer tank to be heated for, let's say, 8-10 hours in a batch process, then at the beginning of the process, we have cold water entering the gas cooler, so low water return temperature, excellent COP. However, at the end of the process, where we already have heated significantly the water tank, then the return water is becoming hotter and hotter, and then the COP is not that great. Let's make a summary so far. There are various factors which influence the CO2 heat pump efficiency. First one is the layout. This is designer's decision. There are various improvements which are well known and proven on the market. There are state-of-the-art technologies and system architectures which have been there for a few years now. So this is not new. Another one is the low water return temperature, which is unfortunately outside of the designer's decision. This is more a function of if we're talking about space heating, what is how big are your radiators or fan coils, or what are the properties of your process heating system in case of process heating. Another one is adequate compressor selection. We'll talk about it in our next section. Control logic. You saw in the previous slide what a game changer could be the evaporator superheat control. This is really important. Other important ones are obviously gas cooler and receiver pressure and temperature control, defrost, heat exchangers, last but not least, hydronic balancing on both heat and source side. Every bit matters when we talk about COP improvements. Let us go into our next section, into the heart of the heat pump. This is the compressor. This is a critical part which needs to perform properly and to be large enough. We have earlier this year approved most of our transcritical CO2 compressors, UL, targeting support the growth of CO2 in the North American market. We have a large application portfolio or product portfolio for transcritical compressors, going to very low displacements. But what are most interesting for us in industrial heat pumps, they are the largest compressors, where we have launched earlier this year in May our new size 6-cylinder transcritical compressor, which at 60 Hz has a displacement of 71 cubes per hour sweat volume. Now, with this new development, we would like to support our partners to build refrigeration and heat pump systems with CO2 in a large size. We can see that easily we have the possibility to build racks of up to 2.5 megawatts, which are 8,500 kBTUs per hour, if I'm not wrong. Pardon for my poor knowledge of imperial units. With few of these compressors, we have projects of this size. So yes, this is definitely possible. Larger compressors are required by the market because CO2 grows bigger in size. So now we are targeting also even further improvement of efficiency and simplicity. So we have launched this compressor in Europe and well, the rest of the world besides North America, because we are still awaiting the UL approval only of this model. This will be at place at the beginning of next year, and we already have offered this one for projects in North America. We expect that our UL approval will be there very soon. Next step, as I mentioned, we are growing in size, is the new development of 8-cylinder CO2 transcritical compressor, which we expect launched in with UL approval 2 years from now, maybe at the end of 2026. This is our target, and there we will have even bigger displacement corresponding to 117 cubes per hour in one compressor. With this new larger compressor, now we can really make a difference and we'll have a complete portfolio to serve all applications, also the very large CO2 transcritical heat pumps. This is our target, to support the business and our partners growing bigger with CO2 transcritical in, among others, heat pump applications. So obviously, size matters. What also matters is performance. We have in all our compressors motor version called SH. This is a dedicated edition for heat pump applications, which gives us extended envelope of the performance. This is targeting, as I mentioned, heat pumps and also parallel compressor. Yeah, but what does it mean exactly for our application? Well, let's put it into perspective. Typically, with minor exceptions, manufacturers of CO2 transcritical compressors, they have limitation in most of the envelopes at 66, 68F. With our envelope dedicated for heat pumps, we have at 77F. So what? What impact does it have on the system? If we have high temperature source or relatively high temperature source, then heat pump specialists would tell you the COP of the heat pump is always better with a higher source available. This is not necessarily true for CO2 heat pump. This is another unique part of the of the CO2, that it turns into transcritical state with low temperatures. Therefore, we unfortunately need to make suction regulation in order to keep the compressor operation within the envelope. So what impact does it have, does the extended envelope have on the system performance? If we simulate in one of our compressors with certain given conditions, what happens with the compressor heating COP, and we vary the saturated suction temperature, where we go with both scenarios, smaller envelope or maximum of 68F and 77F. Well, you see that both compressors improve their efficiency up to the limitation of the first one, 68F, where we see that this compressor's efficiency flattens out because we make suction regulation. If we continue if you continue to utilize this higher suction temperature up to the maximum of the envelope at 77F, the extended envelope, then our performance also improves substantially. Actually, in these conditions, in these assumptions, we see a better performance of 15% if your envelope is higher, 77F versus 68F. Let's make a recap. At the beginning of this session, we are talking that you can fine-tune your COP system layout, make state-of-the-art superheat control. You can have dedicated components for the heat pump, and then still we are targeting efficiency improvement of 12-13%. In this particular application, with a higher source temperature, you can gain even more than that by adequate selection of a compressor, up to 15%. And when we talk about COP, every bit matters, and 15%, that is a good one. That is a good bit. I already mentioned that we are growing large in our compressors. This is not the only component, though, that we are growing larger. We have already a couple of years ago started the launch of our CO2 transcritical industrial valves, where Available in cool selector are already multiple valves rated up to 2000 psi pressure. We also have larger control valves, among others, up to 3 inches, which can be used for high pressure gas bypass valve. But what is really interesting, which is improving energy, is the ejectors. We have had for several years now our multi-ejector available in cool selector. This is or was targeting commercial and food retail applications when it was developed. But if we want to grow in size our CO2 heat pumps, then we need the larger ones. And therefore, in the last couple of years, we have been developing our industrial size ejector, this one over here, which will be launched next year and will be able to support our partners to build racks of several megawatts size. One of these components becomes relevant at capacities above 600-700 kilowatts, and you can have many of those in parallel. This is coming soon, and already now we have opened a couple of projects on the field with it. This will save energy and will really support the industry to gain more efficiency. Again, every drop matters in efficiency, and defrost is not an exception. If air is your source, you must consider defrost. If you decide to use hot gas defrost then there are two ways to control it. One is back pressure control, keeping constant pressure in your evaporator, which means that during defrost process, we have the hot gas entering the evaporator, which is with ice on at the beginning. Then the CO2 gas condenses and goes as liquid through the valve and back to the receiver. However, when there is no ice any longer on the evaporator, therefore no load, then the CO2 gas does not condense and gets out of the evaporator's gas, this gas goes through the valve and back into the receiver and to the compressor, or in other words, hot gas bypass, which is very inefficient for your system during defrost and is penalizing especially systems which are timer controlled. What is more efficient way of control of hot gas is float control, where we at the beginning, just like the former one, we have ice on the evaporator, so the hot gas entering, it condenses immediately. Then there is liquid at the outlet, then entering the float valve, the liquid lifts the float and is being expanded by a deuce to the low pressure side into the receiver. When there is no load any longer on the evaporator, then again gas gets out of the evaporator, meets the float, but the gas is not able to open the float. It stays where it is, which means that we avoid hot gas defrost or prevent it by up to 90%. This is another way to optimize the performance of your CO2 heat pump. Every bit matters and every component matters. Let's look into the heat exchangers. We are launching this year our first CO2 transcritical brazed heat exchangers rated for pressures of 2000 psi and maximum capacity of around 250 kilowatts. This will be launched for gas cooler application and internal heat exchanger. Why heat exchangers are so important? Well, you saw the example of how sensitive is the COP of all heat pumps, depending on your approach in the heat exchanger and on your superheat control. Well, heat exchanger is very important. Plate heat exchangers are the most efficient heat transfer technology. It is also lighter heat exchanger and obviously with a lower footprint than, for example, tubular heat exchangers. So there where applicable, this is a more energy efficient solution. Let us look outside of the heat pump into the water system. Looking into the heat sink, we may have several gas coolers where we heat up the water return to the water supply required, where we store it in a buffer tank or in a thermal storage. It is very important that we properly control hydronically the flow through the gas coolers, but also in the whole ecosystem of the hydronic part. We do that with pressure independent control valves. Over here, they can be seen in different layouts. Similar picture when we flip the view and we go into the heat source side. In industry, you may need to employ multiple sources depending upon their availability. Therefore, you may again need to have a thermal storage. Also on the source side, all of these systems needs to be balanced hydronically. And most important is that we need to have a stable flow and temperature towards our evaporators, so we guarantee that the suction pressure of the compressor is stable, which reduces cycling and brings efficiency in your system. Actually, most of the challenges seen in Europe with heat pumps are not from the heat pump itself, but from integrating the heat pump into a water system by non-specialists into hydronics, as people, as installers, are used to install boilers, but for boilers, hydronic balancing is not critical. Nevertheless, it is critical for heat pumps. So we do recommend to use hydronic control valves, and pressure independent control valve is a good one. Last but not least component, this is the controller. Earlier this year, we have launched our new controller platform called AllSmart. This is a universal programmable controller, which is of the newest generation controllers, which is with way better connectivity or with really good connectivity, which is safe and more reliable to use. It is able to support the entire heat pump ecosystem. And a very important feature is that it is flexible to use, meaning that you can easily expand the IOs, which often is required in different larger commercial or also industrial applications. This is a hardware which we launched. We have been working and will continue working on the development of some application softwares, one of which is available, at least first version is available for CO2 heat pump, but we need to develop many more, and we are looking for co-developing this with our partners. Let's wrap it up. We in Danfoss would really like to support the decarbonization journey of the industry in North America. And we really would like to support with our experience with CO2. You saw um, layout is one thing, but components and adequate selection, they can really make a difference on system level. So compressors for transcritical CO2, valves, precise control, sensors, defining also good superheat, proper controller of the entire ecosystem, many other line components, also control on the hydronic side, heat exchangers, both CO2 up to certain size and water to water. We believe that it is critically important that we look both on efficiency level of the entire CO2 system, but also what can be done on each component, as every job matters. And we would really like to support our partners in this journey. Thank you for your time for now. Let us go into the questions session. Let's see what we have in the chat. Okay. Number one, in which applications can we use CO2 heat pumps? Yeah, there are multiple applications which CO2 heat pumps can be employed. One of which is booming in Europe. This is district heating and large space heating where air is a source. It is very easy to install CO2 as it is A1 refrigerant. It is very easy to accept also in the dense populated areas. So it is fantastic for space heating, commercial heating, and also district heating. Another one is coming more and more, and this is in combined cooling and heating, as I showed earlier during the presentation, where you have, for example, food and beverage or pharmaceutical industry, you have requirements for both cooling and heating. Then we can do that, and we can address both with CO2 heat pumps for both cooling and heating. Then next one, let me see. What is the maximum supply water temperature heat pumps can deliver? Yeah, that is a that is a very long question. It really depends on the technology we utilize for the heat pumps. For CO2 heat pumps, in the typical case of using semi-hermetic piston compressors, I would say very much depending on the return water temperature. Again, up to 90 degrees centigrade, which is 190, 195 Fahrenheit, I would say, typically. Various technologies can be utilized to different temperatures. Let's say that with ammonia, you can target also something in the range of 190 F hot water. With low GWP refrigerants is also up to 190 F as of now. There are various developments in Europe, by the way, generating low pressure steam, which means condensation of, let's say, 240, 250 degrees Fahrenheit. We have multiple prototypes with either some hydrocarbons or with low GWP refrigerants. Are there other factors than COP and investment in selection of a heat pump technology? That is a very complex question. We engineers, we look primarily into the COP, but this is wrong. Ideally, we need to look into total cost of ownership over a lifetime, but this is a way too complex for the industry to figure out. Therefore, we can say there are various factors that must be considered and can be considered in a handy way. COP is the first one. Not the only one, though. Next one is investment. Depending on technology, depending on the application, you can have better fits and worse fits for your system. Then legislation, obviously, you must consider what is the legislation. In some regions, it is easier to accept certain refrigerants than others. CO2 is everywhere accepted on the globe, also in most populated dense areas, which makes it really, really easy. Then flexibility of use, as I said, we need to be able to disconnect cooling and heating if we have industrial process requiring both, but also how fast can you ramp up your system. If you need a fast response, then a CO2 rack can be a very flexible solution with several compact compressors, with several cylinders. You can develop actually a very good algorithm which safely can turn on all of your compressors, giving you, let's say, 2 megawatts, again, around 8,000 kBTU per hour, very quickly in a matter of a few minutes. While if you get one very large compressor delivering this large capacity, it's probably not going to live very long if you turn it on in 5 minutes. So these things also need to be considered. There is not one right answer. There is not one superior technology which is better than all others. We always must consider the application, look at our application, all fits to this application from technology, and then base our selection on various factors, not only COP. Let's look into the next one. which is the best heat pump technology for industrial applications? I think I just answered this one. Apparently, there is not one diamond solution which is superior to all others. There is place for every technology. Every technology has its advantages and disadvantages and fits better than others into certain application. We have time for one more. Let's see. Heat pumps are relatively new in North America. Are they a mature technology in at least Europe? Yeah, well, heat pump technology is more than 100 years old. In Europe, there are heat pumps which were installed already 100 years old ago in Switzerland, also from the 70s, 80s. In Scandinavia, there have been heat pumps. However, because the market was not there, because of favorable conditions for burning fossil fuels such as natural gas and high electricity price, they have not been really deployed massively. However, the technology has been there for many years, and what we saw in Europe over the last 10 years, heat pump market growing immensely, very fast. Decarbonization is one thing, but it's not only about decarbonization. If you connect your cooling and heating in processes, then it is actually a good business. Again, with the large deployment of renewable energy sources delivering very cheap electricity, we really see that installing heat pumps can be a big benefit and also very efficient for the business. There are more questions, yes, but I don't think we have more time for them today. We will reach out to you later on with our replies, and please feel free to reach out to us with any comments or questions. We would like to go once again through the heat pump topic in North America and support you in the best way we can. Thank you for your time.